this one, and I'm already recording it. So last time we talked about this actually. Last time we said that, okay. Remember our hierarchy? This, okay. This was the picture that we used last time. We said that employee is a class, base class, but abstract base class. Why is it abstract? It's abstract because I cannot specify the function earnings. The function earnings doesn't make sense for the employee because I don't know how much an employee makes. Okay, so that's why we said that let's keep this employee class an abstract class because this is going to be a pure virtual function. I expect this function to be overridden in the derived classes. Okay, so print is another virtual function. I know that it will be overridden by the derived classes, but it has some meaning for the abstract class employee because I can print at least the name and the social security number. Okay, this much I know. This much I know. So this was the hierarchy. We developed this hierarchy. I'm not going to look at the details of these classes, but I will directly go to the driver code with the main function that uses all these classes. Okay, so this was the case, line 22 and line 23. We are going to demonstrate the polymorphic behavior. Okay, and we are going to send objects of employee pointers and employee references, but there won't be any function like this. Okay, we talked about this. Why? Because you cannot make an object of an employee class directly. Okay, because employee class is a abstract class, nobody can make an object of it and send it as an employee, and I cannot keep a parameter named an employee. Okay, so you might think that maybe they are going to send an hourly employee. That would be right, because hourly employee is an employee, but this one says that E is going to be of type employee. You cannot have that. Okay, so this line is definitely a compiler error. This line is definitely a compiler. You cannot do that. Okay, so we looked at this. We said that I have 1, 2, 3, 4 objects of derived classes of employee, and now I am calling this print function, which is the virtual function, also the earnings function, which is again the virtual function that are defined in the base class. All of them are static binding functions, early binding functions. This is the answer to your question, right? So the fact that print and earnings are defined as virtual functions doesn't mean that they all will be late bound. Okay, they will be statically decided during the compile time, if you call it this way. The only way you make a polymorphic call is either through a pointer or through a reference, like these two. So the parameters for these two functions, inside those functions, since I am using this employee pointer or the employee reference, I'll be making polymorphic functions inside those functions. Okay, so that's what we said last time, and that's our classmate is asking about. So from line 41 to 50, everything is statically bound. There is no late binding. But when we come to this, the second part of the code, I make an employee pointer vector, and I place pointers of my objects one by one inside this vector, and I made this call. See, virtual via pointer. Let's look at this virtual via pointer. Virtual via pointer is very simple. It just make this call, just print call, but it is using the base class's pointer. Okay, so if print is a virtual function, then this is going to be late bound. Okay, and that's what's happening here during the runtime, not compile time. During the runtime, we are making out of all those 5 print functions. There are 5 print functions. Out of all those 5 print functions, which function is going to be called? Okay, that's that's decided during the runtime. Who makes that decision? Our code makes that decision. Compiler produced the code, okay, a simple code, but nevertheless it's code, okay. Compiler produced that code. That code follows this pointer and inspects the object itself and finds its type and calls its print function. That's why late binding functions are a little bit expensive. Not much, but a little bit expensive. It is more expensive than statically bound functions. Okay, the same thing again, virtual via reference. I am going to do this. And they couldn't write a function like this, as I said before. They couldn't write a function like this. They couldn't put it under here. Okay, they couldn't put it under here. Why? Because, as I said before, if I do this, I have to make an object in my stack. Remember what happens when you make a function call? An employee object is created on the stack, right? There is no way to create an employee object because the employee is an abstract class. So, I mean, I cannot write the third one like this one. I couldn't say base dot employee dot e print or something like that. No, I can't do that. Okay, so this is what happened last time, and we had a question at the beginning. I answered that. Are there any other questions? First of all, let me make sure if I am recording everything right. Yeah, this one is okay. This one is okay. Am I good with the space? Where is my? Yeah. Good enough. Good. Okay, any questions about the polymorphism? As I said before, we did this. Okay, we are doing this. Usually, I mean, the more advanced the topic, more difficult it becomes to give you nice and understandable examples in a few slides. Okay, that's why the examples we give you are these kind of stupid employee hierarchy, shape hierarchy, and etc. You might ask who in this world uses this kind of programming in their professional life. You are right. These are simple stuff. Okay, these are simple stuff. But I cannot go any more complicated than this because it's going to take 2 hours to tell you the example. So that's why we give you. But at the beginning of the chapter, I told you the polymorphism, one of the most widely used features of object-oriented programming, by giving this WinApp example, right? To make a Windows application, you have to drive your class from the WinApp base class, okay, which is an abstract class actually, kind of an abstract class. Well, let's call it an abstract class. And in order to make a Windows application, you need to override some of the functions. Once you override them, you are fine. Your application will start running. It will compile and run. Okay. And the nice thing is, you don't have to do lots of stuff that usually people do when they write Windows applications, because your base class handles most of the complications of writing Windows applications. Okay, and when we start talking about Java, okay, at the end of the Java discussions, I will tell you about how to write graphical user interface applications with Java. It's just an example, actually, just to show you. It's a library. It's a very large library, graphical user interface library of Java. It is nicely written. They obey almost all the object-oriented rules. So we are going to analyze, we are going to inspect those libraries, and you are going to see how polymorphism and inheritance is very useful in writing brief code meaningful code, and how object-oriented programming help us in the concept of reusable code. Okay, we keep using the same thing over and over again without writing much code. Okay. Yes.
If employee class doesn't an abstract class, then this function's valid.
Yeah, if employee class is not an, let's say, let's modify this code. Let's go to the line 65 and let's do exactly whatever you are suggesting. You are saying that, why don't we do this? Okay, instead of just doing this, let's write return 0, right? Now employee is not a abstract class anymore, right? It just returns a stupid number 0.0. That's it. So your question is this compilable now? If it is compiled, so what happens? Let's go there. Where is my, yeah, here it is my code. Now it is compilable. And if I write this code, void f employee e, and I am going to say e.print. That's first thing, that's what they do, right? Then I will say cout e.earnings. Okay, that's it. This will compile, this will run, but every time I make this call, okay, employee e, this print and this earnings will come from the employee class, definitely. Because why? These are not polymorphic calls. These are early binding calls, and they are decided which function to call will be decided during the compile time. Because our rule is to be able to make a polymorphic call, the first function has to be a virtual function. Print and earnings, yeah, they are virtual functions, but they have to be called through the base classes pointer or base classes reference. This one is not. By the way, when I say base class, every class can be a base class, right? I mean, remember our commission employee is a base class to the base plus commission employee, right? So so every class could be a base class. So that's so don't expect that I didn't call this function using the employee base classes pointer and etc. No, well, that's not the case. I mean, for all the other classes could be a base class to some other class. Okay, did I answer your question?
I want to ask why they decided to use reference or pointer to make late binding or virtual calling.
Why did they decide it in 1988 this way? Make this function called polymorphic if they are through the, is that what you're asking? Why they decided, why they designed the why did they design the language this way? Is that your question?
Yes, I mean, for example, why this this format does not call the other earnings functions?
Well, because this employee is an employee, okay? There could be nothing more. This is an employee. This one could point to a commission employee or hourly employee or base plus commission employee. This one can be a reference to, okay, commission employee or hourly employee or any other class that derives from employee. This one cannot. This is an employee object. It has to belong to that class employee, okay? Because this is the class itself, okay? Well, you might say that if I call this function with an hourly employee, yeah, hourly employee stays in an hourly employee. This is another object, okay? This is called by value. This is not called by value. No copy is made. No copy is made with this one, okay? Employee object stays the same. I am here keeping an employee pointer to point to that object, okay? And I am keeping an employee reference to that object. That's the reason. Okay, that was a good series of questions. Thank you.
Like a void pointer.
What?
Like a void pointer in C.
Like a
void pointer.
Like a void pointer. Yeah, well, it is not. Void pointer can point to anything, right? But employee pointer can point to only employee and right classes only. So it is a very restricted void pointer if you like to see it that way. Okay. So employee pointer can point to only employee objects, hourly employee objects, or base plus commission employee objects, and etc. Void pointer can point to anything. So it is the most generic code that you can write is the function that takes a void pointer and returns a void pointer, right? So those are the things. Right? It's like, I mean, this malloc function is very, very, very generic. Or you know that in C we have this sort function, right? The generic sort function in C sort function. So this C sort function, I am sure you have seen this in. Let me try to find. Yeah, okay. So this is the header for the C sort function. It takes a void pointer base. How many items do you have? What is the size of each item? What am I gonna use to compare the items? So it takes, again, this function too. It takes void pointers and a function pointer. So this is as generic as it can get, because it doesn't talk about it's going to sort a day of year object array, or it's going to sort a double array or a Boolean array, whatever. Okay. So the point I am trying to make is that void is the most generic type that you can have. But sometimes, most of the time, we don't want to be this generic. We like to constrain our programming environment. We say that, okay, this virtual via pointer function can take lots of pointers, but all those pointers has to be from classes derived from the employee class. Okay, good. Okay, let me move on then. We keep talking about this polymorphism is nice and etc. When we say that polymorphism is good, but it requires late binding, and late binding is decided during the runtime, and it is expensive. That's what we said, right? So let's talk about this expensiveness. Okay, let's talk about this expensiveness. This is what happens when I do the polymorphic call. Remember, I have 4 objects. Okay, one object is the salary the employee. The other one was the hourly employee. The other one is a commission employee. The other one was the base plus commission employee. 4 objects. Okay. In order to make the polymorphism possible, each class, not each object, each class holds a virtual function table. Okay. Inside the virtual function table, it keeps pointers to virtual functions. Okay. Employee class is an abstract class. It has 2 elements in its virtual table. One is the earnings. The other one is the print. Earnings element doesn't point to anything because I did not implement the earnings function. That's why it is null. But employee class has a print function, and print function is somewhere in the memory during my compilation. Okay, and this table holds a pointer to that function, and we say that, okay, we say that by looking at this table, I can find where the print function of this employee class is. So this employee class keeps a table, and this table is alive during the runtime. This table is not just for compilation time. It is alive during the runtime. So polymorphism takes some CPU time. Also, it takes some memory too. Salary the employee, again, it has to keep this V table, virtual table. As soon as you implement the salary employee class and override earnings and print function, this table is changed. My earnings now is pointing to this earnings function of the salary the employee, and my print function is now pointing to print function of the salaried employee. Okay, so we keep repeating this. We keep repeating this. So during the runtime, I have this table. I am keeping it for each class. Again, I am repeating. It is not for each object, okay? It is for each class. It is for each class. Okay? And remember this, when I say, okay, employees one, this is an employee pointer array or vector, and I have 4 pointers in it. When I say employees one print, employees 0, 1 is here. This is an object, okay? This is a pointer. So the our code, not the compiler, because this is runtime, there is no compiler anymore. Our code follows this pointer, okay? So it's a pointer to the base class, that is the employee class, okay? It is a pointer, it says that my object is here, hourly employee. So I found my hourly employee object, and I go to the virtual table of this hourly employee object, and I find the print function that hourly employee object, and I call it. So how many times I looked up? I looked up this one. Okay, I found the object, and after the object, I determined its v table. I go to the v table, and I now know the print function. Okay, so finding the object, I am going to find the object anyway, right? Because this is an employee. This is a pointer arrow call, a function call through the pointer. So I am going to find this object anyway. After finding the object, I determine its type, and I find this v table. Inside the v table, I make a search. I just find the print function and I call it. So this step and this step is extra. So 2 more memory lookups. Instead of just 1, I need to make 2 more memory lookups, and that's going to cost me some CPU time and a little bit more memory. Okay, so that's what's happening. That's why when they say that when you're writing in C++ code, they say that be careful when you are using the virtual functions, because they will cost you a little bit of time, they will cost you a little bit of memory. So be careful about them. So if you like to make a virtual function, you make it virtual, but be careful. In Java, they say that everything is virtual, we don't care. Okay, in order to make a function not virtual, you have to say it specifically. The default behavior in Java is for all the functions being virtual. Okay, so if you don't like that idea, then make it non-virtual by using some mechanism, and we are going to show you that. Okay, if I go to this compiler explorer, I am going to write this. Okay, can you see that? No, you can't. Well, I don't need this code. Let me get rid of it. Let me get rid of this one. My code is here. Okay, it's a very simple class. It is just a class, and let me do this. So it's an empty class, nothing in it, and I run this program. It just prints the size of A. What would you expect the size of A being? What would you expect the size of F in this case? Because A doesn't have a data member in it. A doesn't have any functions. What would be the size of each A object?
0.
What?
0.
You would expect 0, but that would make it a little bit difficult for the compiler to keep track of the addresses of the objects. Why? Because if I have an array of A's, right, what would be the difference between the first element and the second element, right? They would exactly point to the same location. That's why if you do this, the size of I'm running it. When I run this is what I get. Okay, it just prints 1. Okay, it just prints 1. Doesn't matter if I have a function in it, because functions are not added to the objects, right? This would have been a very complicated function. Doesn't matter, its size is 1. But if I just, let's say, keep an integer in it, integer a, now it became 4, see? Because it has an integer in it. It is not 1 plus 4, because 1 is 4 is just a dummy location. Just to, I mean, we cannot have objects of size 0, because if I have an object of size 0, and if I have 5 of them, they would share the same location, right? Because their sizes are 0. That wouldn't be good, okay? So that wouldn't be good. So now I have, since I have an integer, I don't have to use that trick anymore. So my size of each a is 4, okay? Now I got rid of it. Again, my size is 1. How about this one now? See, I make it virtual. When I make this virtual, what happened to this number? Can you guys see it from back there? I'm not sure. Yeah, okay. It become 8. Why? Because I had to add a pointer to the v table at each object, in each object. Each object, like this slide here, has to keep a pointer to a v table. I am not saying that each object holds a v table. I am saying that each object holds a pointer to the v table. Okay? So if I keep adding more stuff like, okay, F2 and F3, okay, I have them, all of them, okay, I am still returning 8. I am making the v table large, but the object size doesn't get large. Why? Because the object keeps a pointer to the v table. Okay, that's what's happening. So polymorphism is a little bit expensive because you need to make a lookup inside that v table. You need to find it, and it needs just a little bit more memory, because at each object you have to keep at least 8 bytes of pointer to get to the v table. Okay, any questions about how this stuff works, about the v tables? This would be a very nice, actually, let's say you don't have polymorphism. Let's say you don't have polymorphism in, yeah, we don't have polymorphism in C, right? How would you implement the polymorphism? When you drive a new class from the base class, you have to keep the v table inside your class, and every time you make this derivation, you modify your v tables yourself. But during the runtime, all the function calls are made by. Maybe this would be a nice bonus homework. Yeah, maybe I should do that. Okay, let's go back to the slides. These are my slides. Yeah. Okay. Good. I added these slides, by the way, to the Teams page. You can check them out in those pages. Okay, good. Cost of polymorphism. Okay, in C++. The cost is negligible. I am sure somebody made this check. I couldn't find it, but I think if you are doing this in a loop, you are going to see that, well, I mean, you are going to see that it's going to cost you if the function is small, etc. Well, we shouldn't always trust people answering stuff in Stack Overflow, of course. VF table, it doesn't give me any numbers. Yeah. By the way, you are going to see this in your 4th year classes when you do the object-oriented design. Some people don't like inheritance, they say that don't use inheritance, okay? Ignore the is a relationship. Keep the is a relationship in your mind, okay? Use composition, okay? Use just composition. That's what we should do, they say. Okay, so let me move on and let's go and let's talk about our slides. Where are our slides? Okay, so these are the slides of the book. We came back, and I think at this point we have stopped talking about our book's slides, and let's go back to them. And now we know these, right? We have now on the left side, those are the things that we have learned up to this point, up to the polymorphism chapter. Virtual, okay, no, sorry, on the right side, these are the things that we have learned before the polymorphism. Non-virtual functions, okay, we didn't call them non-virtual, but they are not virtual. We did early binding all the time. All the classes that we wrote were concrete classes. Now we know how to write abstract classes and how to write functions that use late binding mechanism, and we, of course, without the virtual functions, no late binding is possible, no abstract classes are possible. And in fact, abstract classes are pure virtual function, right? A class that has at least one pure virtual function. Remember when I showed you the when I show you the Java collections diagrams, UML diagrams, okay, maybe this one, and yeah, okay. So when they say, when I said that these are classes, these are not classes actually. When it says interface means that it's a special class that contains only pure virtual functions. Okay? That contains only pure virtual functions. This iterable or this collection doesn't have any functions implemented. In fact, this class doesn't have any data members, non-static, non-constant data members. Okay? So these are the abstract classes. Abstract means what? Some of the functions are defined, some of them are not. And these are the concrete classes. You can have objects of only the red stuff. Okay? You can have objects of only the red stuff. The blue stuff is not instantiable because instantiatable because it is. I mean, this is an abstract class. This is way more abstract than abstract class. This is called interface, and we are going to talk about it. And they are very useful. They are very useful. So, and there is one principle, object-oriented programming principle. Object-oriented programming principle. It says, write code against interfaces, or let me say interfaces. Okay, interfaces. Okay, interface means that a class that doesn't have any functions implemented. There are function definitions in it, the function headers, but it doesn't have any function implementations. Why is this such a good idea? Because if you write your code, I mean, if I am going to choose a class in this hierarchy to use in my class, okay, it says that choose a class from the upper levels, either iterable, collection, set, sorted set. Don't use any of these stuff. Because if you use any of this stuff in your classes, you are dependent on this class now, right? So if somebody makes a change in this one, you have to change your code, okay? Or better yet, if you write your code against this one, if you just use this class only, okay, so later you have a possibility of switching your class from this one to this one, or that one, or that one, or that one, or any of the descendants of this class, right? So you are writing very generic code. if you are writing your code against this class, you can put any class in the collections hierarchy in your class after. You can change it. So write your code as generic as possible. That's the rule. Okay, that will make your code simple. Your code will depend on less number of classes, so you will be more flexible for the later modifications of your code. Okay, so that means what? In order for the people of your clients, in order for them to write generic code using your code, provide these kind of classes. A class that doesn't have any functions implemented. Okay, that's what you are going to do with your new homework number 5. Okay, you are going to write a base class for these two-dimensional board games. Your base class doesn't know how to play the game. It knows that the game has to be played and etc. And that's what you are going to do with that homework. Okay, let me go back to the slides again. Object-oriented programming principle. Okay, try to use these ideas. Try to write abstract classes as much as possible, and if you can make it, don't implement any of your functions. Okay, leave them to later implementations. Of course, without obeying all the object-oriented programming principles. I mean, if I don't implement anything in the base class, and if I push them to the derived classes, all those implementations, and if I end up copying and pasting same code in all the derived classes, then that's not a good thing. Okay, I cannot trade one object-oriented programming principle with the other one. I have to obey all the rules. So we have to be smart. We have to study lots of other code. Okay, let's move on and let's talk about this slide number 20 maybe. Okay, so I am going to skip this more stupid example of class of the book, this discount sale and etc. We already looked at this employee hierarchy. It was much better than that. Okay, so the virtual functions. The book says that they are like magical, but in fact they are not. Okay, so that's what we say. We write our code way before our derived classes are implemented. We can say that, right? We can do that. We can do that. For example, that main function, or remember this one? Remember this one? Remember our main function inside the if I can find it. Anyway, our main function inside the hierarchy, our main function didn't talk about especially those functions, virtual via pointer, virtual via reference. They didn't talk about any of the derived classes. It just talks about the base class itself. That's it. That was it. So I write that function, those two functions, way before I write the hourly employee class and etc. So I'm writing a generic code. So that we are talking about, and this is how the virtual functions work. It's not magic, it just uses the virtual tables. Okay. And some terminology. We talked about this before, but let's talk about this again because it is important. Okay. When you redefine a function from your base class, we know about this from last chapter. Okay. But if you do this redefinition for a virtual function, it is called overriding. Okay. Overriding is used for the virtual functions. If you change a virtual function, re-implement it again, okay, it is overridden. But if you are re-implementing, redefining a non-virtual function, it is called redefined. Sometimes people use these two interchangeably. That's okay, but we try to use the correct term. Okay, if you don't, okay, if you are confused, if you say that, okay, I have a class sale, base class, discount sale derives from sale, okay, And when you do this, when you say double bill const, I know that I am overriding this base class function bill just to make sure that I am not redefining, I am overriding. I put this keyword override. You are telling the compiler that I am overriding a base class function. Okay, so just let me know if I am making a mistake. If I didn't have this virtual keyword here, this would have been a compiler error because there is no overriding of the base class functions. Okay, there is no overriding of the base class functions. Okay, so if I say override, then that means that I must be thinking that the bill is a virtual function. In fact, it is not. Then this would have been a compiler, but it's not because bill is a virtual function. So it's a new C++ 11 edition. It's called override keyword, and you can use it here. Okay. Another similar keyword that we use with the inheritance is the final keyword. Okay. If I say that I have a class sale, it has a bill function, a virtual function, and if I call this function as final function, then nobody can override it anymore. Final means that it is not overridable. Okay, you cannot override it anymore. It is virtual, yes, and it's a base class function, yes, but nobody can override this anymore. So if you do this, it's a compiler error. It's a compiler error. Override is prevented by this keyword final. Okay. So it's lots of crowded stuff. This is virtual here, const here, and double here, and final there. Just the function name is here, but it's the way it is, right? Okay, so two useful keywords. Again, these are useful keywords. Once you have your program compiling and running, no problems. If you remove these final keywords or the override keywords or that kind of stuff, then your program will keep running, and you understand that. If I remove this keyword in a running program and compile it again, it will run and compile, right? No problem if I remove it. Same with the override keyword. So those are the keywords that are useful for us as programmers. These are kind of ways of getting help from the compiler if you make a mistake. Can I do the same thing with the virtual keyword? If I have a program of 10,000 lines, I have lots of virtual functions, okay? I know that the program compiles and runs fine. If I remove all the virtual keywords, would my program compile and run? The first question, would it compile?
No.
How many people says yes? How many people says no? Are you saying yes? It would compile. Just one people says yes, it compiles. All the others? How many people says no? Just one no? It should compile, right? Why? Because let's go to the code. I don't have the code. Let's go to the, think about the code in my employee class. In my employee class, I have the print function. In front of the print, there was a virtual keyword. If I take it out, all of my print code will become static binding examples. So it will be static binding, but it will still compile. Okay, if I remove the virtuals. Maybe the one case would be pure virtuals. When the function is pure virtual, okay, you don't have to implement. You don't implement it. But if you remove the virtual keyword there, then you have to implement it. In that case, you may get a compiler error. But anyway, okay, most of the time it will compile if you don't count the pure virtual case, but they will not run as before. Why? Because there is no late binding anymore. It will be all static binding, and that will be a problem. Okay. So the kind of the difference between virtual and final. Okay, so if virtual functions are so useful, why don't we use them all the time? That's the question. So that's the answer is, of course, obviously overhead of use storage, and overhead of CPU time, a little bit slow. Okay, if you don't need the virtual functions, then don't use it. Okay, that's the idea of C++. Java says just the opposite. Okay, virtual functions are so efficient. They are not that expensive. So use them all the time. But if this bothers you, okay, just let me know. If this bothers you, I will turn off the polymorphism for your methods if you don't like it. We are going to see it. Okay, we talked about the pure virtual functions. Okay, pure virtual functions is the ultimate virtual function, which makes the idea of abstract classes possible. Again, abstract class is something weird, but something possible too. You are making a new type, but you cannot make objects of new type. Where am I going to use this? Of course, you are going to use it as a base class for an hierarchy, right? Base class as a hierarchy. You are designing your class, but you cannot fill in some of the missing parts. It is not possible. I don't know what to return for the earnings of an employee. I don't know, so I am not going to implement it. I don't know what to return as the area of a shape. What is the area of a shape? Okay, either I am going to return a stupid 0.0 or minus 1.0, or I will say I'm not implementing this. Not implementing this is a better idea. Okay, so more abstract level of writing code, more efficient you are going to be. Okay, people have invented numbers, right? So what was wrong with these numbers? 1, 2, 3, 4. These are fine. They had to invent this number 0, which is very meaningful, which is not very meaningful. Just there is no such thing as 0, right? There is no such thing as 0. There is 1 and 2 and etc. So they added this more abstract level of thinking, and with this now I can write this kind of stuff, 102 and etc. Later they invented this, right? Why don't we do such and such and such? And they have invented this because this is a very difficult number, so the rational and etc. And one day it came that, well, we cannot do stuff like this one. How about this complex number, etc. So you are using more and more abstract stuff. Maybe it is more difficult to understand, sometimes difficult to use, but using this kind of notation makes lots of things possible that are not possible with these kind of very primitive numbers. Okay, very primitive numbers. So it is up to you if you like to invent a new number set. Okay, a number class, and use it in your calculations, scientific calculation, programming calculations. If it is not useful, then you are writing bad code. If it is useful, if it is reusable, then you are doing something good. Same with the programming again. Try to think abstractly at some degree, but if it makes things a lot more difficult than it used to be, then you are not doing it right. So again, you can go right or you can go wrong with the abstract functions or the inheritance. If you are doing it right, they are very useful. If you are not doing right, then you are in trouble. And the worst is your customers are in trouble. Okay, let's take 15 minutes of break. Let's be here around 10:38. 10 minutes. I forgot about the attendance. When we come back, I will give you the attendance.
Bilmiyorum ama ameliyatını biliyorum.
Bir şey denk geliyordu. Sıkıntılı bir şey var.
Devrede yapıyor.
Okay, so let's talk about this extended type compatibility. There is an is-a relationship between the derived class and the base class. We know that the is-a relationship is a directional relationship. It is not symmetric. All the discount sale objects are sale objects, but not all the sale objects are discount sale objects. Okay, and we are going to give this example just to explain our ideas. Okay, we have a class pet. Okay, very simple class. We are not going to obey the rules of object-oriented programming. We are going to make everything public so that the example stays very, very simple. Okay, the idea is to use the inheritance now. We have a class pet. Okay, pet has a very simple class. It has a virtual void function print and a name. And we have a derived class dog. Dog is again very simple class. It has just has a new string breed. Of course, it inherits all the members of the base class pet. Okay, and of course it is overriding the base class print here. Okay, so that's a very simple class, and we are going to do some experiments with it. Okay, I can make an the declaration like that, and let me in fact do this. Okay, this is v dog, and another one is v pet. Okay, inside pet I have only the name. Inside dog I have the name and breed, right? Two things. This is what's happening. Okay, this is what's happening, and let me copy this. Maybe I can use it later. Okay. Okay, let's look at this picture now. Okay, let's look at this picture now. We are doing this. Remember, we have a pet and we have a dog. And when I say v.name gets the value of tiny, v.name gets the string tiny, and then v.breed sorry. Okay, v.name is tiny, v.breed is Great Dane. Okay, and then we assign vpet to vdog. So let's look at this more carefully now. I can do this. This is an easy relationship. I can do this. This is an easy relationship because all the dog objects are pet objects, so I can do this assignment. Opposite is not true. Okay, opposite is not true. Not all the pet objects are dog objects. I'm not saying pet objects are not dog objects. I am saying not all the pet objects are not dog objects. Okay, so the opposite is not true, and I am not going to make this possible. A compiler will tell me that I cannot do this assignment, but this assignment is okay. But when I do this assignment, this is what happens. Inside vpet, I have only space enough for name. Okay, but vdog has space for name and breed. So when I do this assignment, I am only assigning this name part only. The breed part goes away. Okay, the breed part goes away because I don't have the space. Even though I am doing this assignment, I am losing some data. It is like when you assign a double to an integer, you lose some data, right? And it's something like this is happening here. This is called slicing, as some people call the slicing problem. Although it's not a problem, it's just a feature, right? This is slicing. I sliced out some part of the object when I am doing this assignment. Okay? Although I can do this assignment in this direction, I can assign dog objects to pet objects. That's possible because it's a relationship. But when you do this through the objects, through the normal assignment, then this slicing problem will occur. Okay? Or the slicing will occur. Okay? I cannot do just the opposite way. So it will be gone. So this is called the slicing problem. This is called the slicing problem. Okay? Notice value assigned to vpet loses its breed field, breed data member. Okay, this is called slicing problem. Okay, well, I mean, if you are doing this assignment, you agree on this anyway. So what are you gonna do? You can, I mean, if you are going to do this, then you should know the consequences. And in fact, I mean, although we don't like it, we kept assigning doubles to integers, right? We know what's going to happen. I mean, if I have a double 2.3 and I'm going to assign it to an integer I know that I am going to lose some data. I know that, okay? So if you know what you are doing, this is not a problem, but you should know about it, and it's called slicing problem. Some of you might say that, why don't we use pointers? And I mean, if you use a pointer, okay, to assign a dog pointer to a pet pointer, no data will get lost, right? Because it's a pointer assignment. Let's do that. Let's do that, okay? Now I have this picture. I have a pet pointer and a dog pointer. Okay, it looks like I made another derivation here, a cat class. Inside the cat class, I have the eye color. So I think this is more clear now. I mean, all the dog objects are pet objects. All the cat objects are pet objects, but not all the pet objects are cat objects. Okay, not all the pet objects are dog objects, right? Just the opposite is not true. Okay, so this is what I'm going to do. I have two pointers. P pet and P dog. Okay, one of them can point to the pet, the other one can point to the dog. And I made a new dog object, new dog. Here it is. My dog is here, P dog, okay. And P dog name is, why don't I form this picture again? Because while I am doing this, everything will be clearer. Okay, so this is my memory. I have two pointers. P pet and P dog. Okay, and then when I make a new dog object here, okay, and P dog is pointing to this one, and P dog name is going to be name is going to be Tiny, and breed is going to be Great Dane. Okay, and then I will do this assignment. P pet gets the value of P dog. Can I do this? Yes. Why? Because there's an is a relationship. So P pet is pointing to this one. I can't do the opposite. I can't say P dog gets the P pet because not all the pet objects are dog objects, right? They get the same thing. So I know that both of them are pointing to the same object. This is all valid. Compiler says I am fine. Yeah, well, you can do this. No problem. You can do that. No problem. Then let's write some code. If this is possible, can I do this then? C out P dog arrow name. Sure, why not? Because P dog has a name field in it, and I can print this out. How about this? C out P dog breed. Is this possible? Can I write this? P dog breed? Yeah, no problem. How about this? C out P pet name. This is possible too, right? Is it? I am using just a P pet pointer to point to this object and writing it there. Okay, no problem. How about this one? C out P pet breed. This is possible. Okay. Is the last line possible? Can I write this? No. Why? Because if you are the compiler, you are compiling this line. I am going to print something that belongs to a pet object, okay? So I follow this, I find this object, it's a pet object. If it's a pet object, let me go to the source code for the pet. Well, source code to pet says that it has a name field, name data member, but it doesn't have a breed data member. So I can't do that, right? I can't do that. So this is going to give me a compiler error. No, you can't do that. You might say that, well, I am seeing it. I mean, during the runtime, I see that this ppet points to a dog object actually. So although it is correct that not all the pet objects are dog objects, in this case, this pet object is a dog object, right? But the compiler wouldn't know that during the compilation time, right? During the compilation time, compiler can only say that inside a pet object there is only name, there is no breed. I can't compile that. Okay? Compiler doesn't know that this one is not pointing to a, for example, let's say another pet object here, and its name is its name is Boncuk. It's a pet object. So this p pet can point to this one, and in this one there is no breed, right? So the compiler wouldn't know if it is pointing to a pet object or a dog object. So again, with the pointers and references, no slicing occurs, but you cannot reach that part. You cannot reach the part that is hidden from you as a pet pointer. As a pet pointer, you might say that, why don't I do this then? Maybe I can do this, right? Maybe I just right after this, what did I do? I said that at the beginning. I said that p pet points to p dog, right? That's what I said. That's why they are both pointing to this one. After that, doing this, if I say p dog gets the value of p, or maybe do it another way, dog pointer pd q gets the value of p pet. I am going to make another dog pointer pd2, okay, and I like it to point to this one, and I am going to assign it this way. But again, this is not possible. Why? Because there is no easy relationship in the other way. Not all the pet objects are dog objects. Okay, so this is not possible. Unfortunately, I won't be able to do this assignment in this case. Okay, so why am I saying this? Okay, why am I didn't say anything new actually. We keep repeating what we have been saying all along. We are just repeating stuff. We are trying to understand it even better, and I am trying to kind of present it in a way that you can ask questions about this. Okay, but what if I want to force it? Then, as I said before, just do this. C is the language of all kinds of opportunities, good and bad. Okay, so I will say convert this to a dog pointer and assign it to this one. So C will gladly accept it and convert it, and you'll do this assignment. You are forcing it. But this is not very nice code, because in this case it's going to work. Sometimes it will give you trouble. Sometimes it gives you very, very bad results, because during the runtime, if you are not sure if ppat is pointing to a dog object, then this is going to give you trouble. That's why don't write this kind of code, okay? Well, although it is okay, don't write this. I don't know, what am I going to do? Just black, kind of a okay, but like that. Okay, compiles, sometimes runs, but if ppat is not pointing, let's say, remember our hierarchy? Cat is another pet class, right? If my ppat is pointing to a cat object, then this will be you'll be in trouble, right? So we need a way of, maybe we need some help from the language itself. Why don't we do this? What did we say? Each object keeps a pointer to a v table, right? Each object keeps a pointer to v table. V table belongs to the class. Then in that case, what does that mean? It means that each object actually knows what kind of object it is, right? So if I go to this object, and I ask, where is your v table? It says here. Inside the v table, there is a field that tells you the type of that object. Okay? So all the objects are actually, if you are using polymorphism, virtual functions, all the objects in C++ know their types. Okay? So you can ask the object, what is your type? And it will tell you, I am a dog object, or I am a pet object, or I am a cat object. If the object is right, then I can do this. Forceful coercion, forceful typecasting. Okay? That's what we are going to do now. Okay? We will get some help from the language, and we will ask the types of the objects. And if the object type is right, then we can convert it, and that's what we are going to do. Okay, let me go to the slides from the detail again, if I can find it.
Sure.
Where is my, yeah, question?
Yeah. Can we initialize can we create a pet object with new keyword inside? Türkçe sorabilir miyim?
No.
Okay.
Can you create a pet object using?
Using new keyword with dog.
Sure. Well, it's a relationship, right? All the dog objects are pet objects, right? So you can say that pet pointer p gets the value of new dog. Is that what you're saying?
Yeah.
Okay. Should I talk to you here? Should I talk to you by looking at the camera?
No, I'm looking at this.
Okay.
I cannot see the paper.
Is that, did I answer your question?
Yeah.
Okay, good. As long as you're happy. Well, I mean, I kept saying this, but okay. Yeah. So let's go to. I mean, why did you ask that question? I mean, this is no different than writing this, right? This is no different than writing this. Why do you think that your question is different than this? You have some other point. That's what I am trying to.
Because they are different pointers.
Well, you said that. Can I initialize a pet pointer with a dog pointer, right?
Dog object.
What I wrote is this. Okay. Pet pointer p gets the value of new dog. This line and this line are exactly the same assignment type. So you see that, right? So okay, so you're not asking another question other than that. Okay, good. Sometimes I miss the question and I answer you, and they are kind of, they don't tell me, but I didn't answer their question. That's why I'm kind of insisting. So let me go to the details slides if I can find them. Where are my slides? Did I close it? Anyway, maybe let's just go to the Explorer again, my browser, and get this work. Yeah, okay, not that one. Detailed polymorphism. Yeah, open it with the draw board. We are going to do this. Dynamic cast operator. Dynamic cast operator cast one pointer to another one if the object being pointed to is the correct type. Okay. Remember, I forcefully assigned one pointer to another one, and I said that this is going to sometimes work, sometimes won't. Dynamic cast does that in a more intelligent way. It follows the pointer and it finds the object. If the object is right type, then it makes this pointer casting, okay? Otherwise, it assigns a null pointer, okay? So this will prevent any crashing. That's what we are going to do. Another operator, again, this is an operator. This is an operator. Dynamic cast is like the typecasting operator. Type ID is like a size of operator. Type ID operator returns a type info object, and inside that type info object, you have information about your object itself, including the class name and etc. Okay, so it is called type ID. It's like size of. When you say size of A, it returns you an integer. This type ID A will return you a type info, and inside this type info, let me show you C++ type info. Okay, yeah, this is better. Okay, so it returns a type info. Inside the type info, I have okay, so it will return the name of the class itself, and I have this equality operator, not equal to operator, hash code, etc. Well, in Java we'll talk about hash code. We will have that kind of information. And this before is compare order of the types. I don't remember this one, but it is interesting. So, what is an order of a type? You can compare two types in the. I mean, is integer greater than a double? I forgot about this. I don't know what that is. So type ID int before type ID character. Oh. So I can compare this. What is this comparison? I don't know. Returns whether the type precedes the type identified or in some implementation specific order. Okay. It is not related to size. Inheritance relationships may differ between programs. So I didn't have to know that. It doesn't tell me anything about it. So it's some kind of a specific order, and you can change this order on your objects and etc.
So this
Yeah.
is 19, maybe C++11 is different.
Well, no, usually you keep the compatibility with the C++11, you add more stuff to it. When you look at this one, okay, in C++11 you have before name hash code, and what is difference? What is the difference? Do we have any difference? I didn't see it. Inside the before, do I have any difference? I think it's the same thing. Yeah. Well, it's a good idea to actually do it. Okay. How about integer and double? Edit and run. No, I'm not going. No. I don't have time. I am not going to spend any time on it. I am not going to use type ID. I am going to use dynamic cast operator, and this is what we are going to do. Again, the same hierarchy. Let me copy my hierarchy from slide number 65 to 104. This is my hierarchy. No. Okay. Take this out and go to 104. Okay. Remember, this is my hierarchy. I will do this. I will make objects of salaried employee, hourly employee, commission employee, base plus commission employee in this hierarchy. And I will use some pointer stuff. Okay, here it is. Employee pointer vector. Okay. And 1, 2, 3, 4 employee objects. They are all created on the heap using the new operator from 0 to employee sizes. Okay. A polymorphic call. Why? Because I am calling the virtual function print through the base classes pointer and this end of line. And okay, so if I do this, I mean, if my loop is just like this, nothing interesting happening here. Of course, I mean, there are 4 polymorphic calls are being called. Okay, 4 polymorphic functions are being called. No problem. We know that. It's interesting, but it is not as interesting as new stuff. Let's look at this one. This is what we are going to do now. Okay. I will convert an employee pointer to base plus commission employee pointer using dynamic cast. I know that inside this vector, there are all kinds of employee objects. Some of them might be base plus commission employee pointer objects, and some of them are not. Okay. I will just attempt this. Without using this line 51 and 52, I could have said base plus commission employee pointer employee I. If I say that, C will forcefully convert this pointer to base plus commission employee pointer. But I know that in this loop, some of the objects are not base plus commission employee pointers. So most of the time, this will be a very bad line because now this right pointer thinks that it is pointing to a base plus commission employee object, and that's going to be a bad thing. That's why I don't do that. That's why I don't do that. I am saying that, okay, follow the pointer, okay, this employee I pointer, find the object. If the object is a base plus commission employee object, then give me a valid pointer, otherwise give me a null. Okay? Otherwise give me a null. So this is called downcasting. Not upcasting, but downcasting. This is our base class, and this is our right class. Okay? I am doing this downcasting. Why downcasting? Because I am trying to convert a base pointer to a right pointer. Okay, upcasting is always okay because there is a relationship there. Okay, but downcasting is something that you need to be careful. So I am doing the downcasting conditional. Dynamic cast operator is very helpful in this case. It will follow this pointer. If it's a, again, base plus commission employee pointer, then it will give me the correct pointer value, otherwise it is going to be null. So I'm going to check if it's a null. Okay, let me get rid of these marks. Okay, I am going to check if the right pointer is a null. If it is null, then I was not successful. Then I am not going to do anything. But if it is not null, then this is what I am going to do. I am going to call this get base salary on the right pointer. Now the right pointer is a valid pointer, and I know that it points to a base plus commission employee object, and I get the old base salary, and I multiply the old base salary with 1.10, so I am giving a 10% raise to this person, and I'm using the set base salary, and I am just printing the get base salary value on the screen, and that's it. So this is my if case. This will work. This part of the loop will work only for the base plus commission employee objects and no other object. Okay, and then line 65, I am just doing a regular polymorphic call. I am doing a regular polymorphic call. Okay, because earnings is a virtual function. Question: is this a polymorphic call? Is this a polymorphic call?
No.
Why not? Why not?
Get base salary is belong to base plus commission employee, not other classes.
Well, that might be correct, but there is one more important reason why this is not a polymorphic call. You are talking about to make a polymorphic call, it has to be the base classes pointer or reference thing, right? Before that, there is something more important. This is not a polymorphic call because
Dynamic casting.
it's not virtual. Get base salary or set base salary are not virtual functions. They are not virtual functions. This is a virtual function. This is a virtual function. And this one is a virtual function here. Okay? Good. What happens here? Instead of base plus commission employee here, if I write employee, would this compile and run? What did you say?
It would compile because there is an is a relationship.
Yeah, well, I mean, line 50 will compile no problem because dynamic cast is going to give you a pointer for the base class commission employee object. Since employee is the base class, there is an is a relation, it will work, but how about line 58? Line 58 says that there is a get base salary function of the right pointer, but the drive pointer type is employee. Employee doesn't have a get base salary. So you will get the compiler error here and here and there, right? Okay? So that's a bad idea to write employee here, but again, we are just experimenting stuff here. Okay? So this loop is nice. Generic code. I run this loop from 0 to size of employees. This part is very generic. This part is very generic. But in the middle, here, okay, in the middle, I write specific code. That code is specific for base plus commission employee objects. So if I like to write specific code instead of generic code, I can do that. Usually you try to avoid this kind of specific code because specific code means specific code. It cannot be generalized. So my code depends on the base plus commission employee class now. Instead of my code working for all kinds of employees, now my code depends on base plus commission employee. I have to include the header file of base plus commission employee to compile this part of code. Okay? So this is specific code, but sometimes it has to happen. Remember my close all function of the base class C Windows app? C Windows app has a close all function, and it just calls the close functions of all the applications using polymorphism, and everybody closes, right? Before I shut down my computer, okay, I call the close function of all the applications. If I want to do this, close all the applications other than the calculator application. What am I going to do? I will write something like this in a loop, okay? In a loop, I will call the close functions of all the applications, but I will make this dynamic cast conversion, and I will say that if it's a calculator one, then I'm not going to close it. Okay? Good. So this is called downcasting, okay? This is called downcasting, and downcasting has to be done in a careful way. You have to be careful. It's very useful if you are doing it right. Upcasting is always okay because upcasting follows from the inheritance rules, follows from the is a relationship. But downcasting is something that you need to be careful of. Okay, not all the base objects are derived objects. Some of them are. Okay, so to check which ones are and which ones are not used, you use dynamic cast operator. Remember, we used the static cast at the beginning of the semester, and I told you that dynamic cast will be coming in a few months. So now is the time. And that's how you know the second type of typecasting, static cast and dynamic cast. There is another one, const cast. This one converts a constant object to a non-constant object, which sounds very weird. Okay, suppose you receive a function, a constant parameter. Remember, we use the constant references. Sometimes it is possible to convert them to non-constant objects. Sometimes, yeah, sometimes you want to do that. Well, that sounds crazy. Yeah, it is, and it is against the rules of principle of least privilege. But sometimes we need to, so that's why we don't. It's like goto, okay? It is available. We don't use it, but it is there, okay? So you read about it where you use. Sometimes if the two libraries are not compatible with each other, sometimes we have to use this. Anyway, Crosscast. So that's the third type of typecasting in C++ 98. Okay, good. So we talk. Okay, and at the end of that one, see, in this loop, I get each employee, their reference set. Okay, this one. What does this return?
Type info.
No. Their reference employee is J. What does their reference operator return? What kind of object does it return?
Employee.
It returns an employee object? It cannot, because there are no employee objects. It's an abstract class. It returns what? It returns a employee reference, right? Employee references are possible. Employee objects are not possible. Okay? So it returns an employee reference, type ID, returns type info object. Inside the type info, I have the name. When I do this, at the end, I will get, okay, salaried employee, hourly employee equals. So each object knows its type by string, okay? If you ask the object, what's your type? It will tell you, okay? But this will be possible if you turn on the RTTI, runtime type information flag of your compiler, RTTI, okay? If this is off, then you don't keep that information in your objects. If you like to save some space, okay, turn off RTTI, so you don't keep that information. Okay, so it's a compiler flag. If you, can I look at this now? Okay, if you, yeah, manual of GCC, and look for the RTTI. So there is a no RTTI option here, no RTTI. Let me find, okay. Disable generation of information about every class with virtual functions for use by the C++ runtime type identification features, such as the dynamic cast and type ID. If you don't use those parts of the language, you can save some space by using this flag. Okay, so no RTTI. By default, I think it is all on. If you turn it off, okay, then you are going to save some space in terms of vtables and etc. Just read the documentation. Okay, so I am way out of my time, but let me finish this chapter by talking about destructors. Okay, let's look at this example. I make a new PF_array_D backup. Remember that one? When I make a PF_array_D backup, okay, I can point to that object using the base class pointer, right? There's an easy relationship, no problem. So I can add elements to it. I can get the use stuff, and when I am done with this new backup class, okay, of course I can't say, I know this much. Of course I can't say PP backup. This is not possible. Why? Because PP is a PF_array_D pointer, right? Base class pointer. I can do the okay, add element stuff, get use stuff, etc. But backup is not possible. Anyway, I can do that. When the time comes, I am going to delete this object, delete PP. So this delete PP, whose constructor is called? Base classes constructor, PF_array_D, whose destructor is going to be called? Base classes destructor or the derived classes destructor? Pointer is a base class pointer. Okay, it doesn't matter. Okay, I did not override or redefine yet used or add element. That's fine, no problem. It is the base class stuff. So when I say delete PP, who is destructor? Base class is destructor or derived? I wish it is derived classes destructor, right? But because that's the correct thing. PP points to a PFRAD backup object, right? But PP pointer is a PFRAD pointer. So unfortunately the destructor of the base class will be called PFRAD. So that will cause what? That will cause memory leak in our backup space, right? It's going to be a memory. That's a bad thing. So to prevent this, what do? We define our destructors always virtual. If the destructors are virtual, this delete PP is a virtual function call. It will determine the type of the object pointed by PP, and it will find the destructor and it will call it. Okay? So the rule number 275 is always define your destructors virtual. Doesn't matter if it is your plan to have a hierarchy or no. Okay? Make your destructors virtual all the time. Okay? So that if you later or your customer derives from your class and use this kind of situation, they won't be in a bad position. Okay? So defining virtual destructors is something that we do all the time. Okay? So a good policy for all destructors to be virtual all the time. Okay, I talked about the downcasting and upcasting. Upcasting again, if you are following the direction of the UML diagram arrow, base class and right class is a relationship is this way. Casting, okay, assigning an object from a dog to a base is okay. There might be some slicing problems, etc. Upcasting is no problem, but downcasting, the other way of doing stuff, this one, you need to be careful. You need to use the dynamic cast operator. And dynamic cast is used with the pointers and sometimes with the references too. But I have only shown you the pointers case. Okay, that's it for today. Are there any questions? Any questions? You guys are scaring me, really. I mean, I got only 2 or 3 questions today. I hope you are having questions in your head and your... Okay.
It's not directly about the classes, but does that mean can I static cast anything to anything?
Well, yes, you are a C programmer. In C, everything is possible. If you don't like it, you just write in your assembly, code in your assembly, and insert that code in your C code. Yeah. You didn't know that? If it doesn't work, assign it to a void pointer, and assign that void pointer to anything that you like, because converting to void pointer is free in C. Yeah. Well, that's a very scary rule for the users of other languages like the Java and C# and that kind of, but they don't know pointers anyway, so. Okay. Good. Okay, I'll see you tomorrow. I will start this new chapter about templates. Bye. Where is my attendance? Bring my attendance here. Where is my attendance? Yes. Thank you. Evet.